Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Stephen Feuerstein, and I'm a PL/SQL developer just like you. This lesson is part of my series on Say Goodbye to Hard Coding, one of the biggest challenges we face when writing high-quality, maintainable code, that is, getting rid of hard codings. The topic of this lesson is Stop Writing So Much SQL. That might seem like a strange topic for PL/SQL developers. Hopefully you'll soon understand why I say this and agree with my recommendations. Some quick reminders. You can download all the code that I reference in my presentation and PowerPoint documents to support the trainings from PL/SQL Obsession, toadworld.com/sf. So if you visit toadworld.com/sf PL/SQL Obsession, you'll find lots of resources for PL/SQL developers. If you click on my demo zip link, you'll have all the files that I use in my trainings. Drill down into trainings, seminars, and presentations, and you'll see PowerPoints that back up and reinforce what I talk about in my videos. In addition, make sure you're comfortable with the material covered in the previous lessons in the series. Start with introduction and concepts. What is hard coding? What's the problem with it, etc. And then take a look at the lessons on avoiding hard codings and declarations, magic values, and more. So stop writing so much SQL. Here's the basic agenda. First of all, let's talk about what the problem is with writing lots of SQL, because you probably don't give it a second thought, which is part of the problem. Why talk about SQL in a lesson on hard coding? That might seem really strange to many of you. And then we'll talk about solutions. And it focuses on the concept and the benefits of data encapsulation, or hiding your SQL. And I'll make a number of recommendations on how to best do that. So writing SQL in PL/SQL. It is by far the most critical aspect of our programs. Why is that? Well, SQL statements directly reflect our business models, and those models are always changing. So the underlying tables, and usually hundreds of them, and the complex relationships between them are the foundation of our applications. SQL statements cause many, perhaps most, of the performance problems in our code. So tuning SQL, the way that we write the SQL in PL/SQL, the way that it performs, overwhelms almost all other considerations when it comes to tuning and performance. So that's pretty critical stuff. Finally, many runtime errors that occur in applications result from integrity and check constraints on tables. So the way we define our tables, the way the data is put into those tables, generally has a lot to do with the error management in our applications. So the structure of the business itself modeled in SQL, critical performance aspects, and lots of runtime error issues. This is really, really important stuff, as I'm sure you'd agree. So what's the problem? The problem is that we take SQL entirely for granted inside the PL/SQL environment. And why not? It's so easy to write SQL in PL/SQL. One of the greatest strengths of the PL/SQL language is, wow, if I need to write an SQL statement, I just write it. I don't have to write any crazy JDBC or ODBC layers of code and stuff that's hard to understand. It's really nice, simple stuff. But that's the flip side. That's the positive. The flip side, the negative side, is that since we take it for granted, we don't set any rules on how, when, and where SQL statements should be written in our PL/SQL code, and maybe even in our Java code and .NET code and so on, which is even crazier. Well, what's the problem with that? Why have rules for something that's so easy to do? Well, as I mentioned before, the SQL statements are involved in some of the critical aspects of the application, how it's designed, what it does, how it performs. And the problem is that if we don't put controls on our code, we end up with a real mess. So generally speaking, when we build an Oracle application, we have our order entry application, or the application code itself that we're writing. We have our low-level tables. And when there are no rules on how, when, and where the SQL should be written, well, at the highest level in our applications, both in the front end and the back end, if I need to get data, I just write an SQL statement. If I need to write an insert a row of data, I just write an insert statement. So we tend to have the same code over and over again throughout our application, lots of repetition, many variations, many different places that we have to maintain and optimize. And that means that we end up with applications that are slow, that are buggy, that are hard to optimize and hard to maintain, because the SQL statements are distributed all over the application. So lack of controls, lack of standards lead to a situation where we have a very hard time managing our code base. Now, I mentioned, hopefully that makes sense to you. Obviously, in the general context of hard coding, you want to avoid repetition. When something is written more than once, you've got to fix it more than once. But let's talk about that in the context now specifically of SQL, because I like to talk about and promote a perception of SQL that every time you write an SQL statement, it's a hard coding. And in fact, just about the worst kind of hard coding you can perform, much worse than hard-coded literal values, which is what everybody focuses on when we talk about hard coding. So why would I call an SQL statement a hard coding? Well, consider a scenario like this. I'm working on my HR application. I need to write a complex query to return data for a report. Maybe it's a 5-way join, a 10-way join. You can all imagine one of your own monster queries. Very complicated, very hard to optimize. I work and work and work and work, and I do it. I've got a page full of SQL, very complicated, but after several days of hard work, I verify that it returns the right data. The performance seems okay, and I use it. And I send a memo out to my team saying, hey, everybody, if you need to get this set of data, here's the description of the data that I needed for my report. If you need the same data, well, here's the query. I'll save you all that time. So Joe needs to use that same query in his business rule procedure, he calls it. Sally down the hall needs to use it for another report. So several different people use the same query. And then what happens? Well, it's pretty inevitable. The 3-way join turns into a 4-way join or a 6-way join. We find a bug. I find a bug in my query. And what do I do about that? Well, I change my query. I fix it. And then I have to send a note out to everybody in my team. Hey, everybody, I wrote that query last week. I found a problem with it, or I needed to enhance it. So please take this query and replace your query with my new query. Well, what if Joe's out sick that day? What if Sally's mad at me for something I said at the meeting and she doesn't want to listen to anything I have to say? The bottom line is we can end up with multiple occurrences of the same query, but now in varying states. One of them is updated, another one is fixed, maybe fixed in the wrong way, another one is never changed at all. Even if you find all the occurrences, which is a very tough thing to do, how do you keep things in sync? And beyond that, chances are you're never going to be able to find all the occurrences of the quote-unquote same query. Taking a step back, this process of assuming that something's not going to change, here's my query, this gets the data you need, so use it. What I'm saying in that statement is, and it's never going to change. We're always going to get the data in the same way. And then I have that same statement in multiple places. It's exactly the same scenario as referencing a literal value in multiple places. For example, in the introduction and concepts lesson, I talk about and show this piece of code. And I mentioned that you've got 1 million here, you've got 1 million here. Obviously, you don't want to do that. And everybody agrees. We all know you don't want to do that. Well, if I have this select statement here, and I have it in another procedure and another function and another report, that's even worse. It's the same problem. I've hard-coded a part of my business model, and now I have multiple instances of it, and I can't even find them all, much less keep them in sync. So from a logical standpoint, there's really no difference between hard-coding a literal value and hard-coding a select statement, except that the select statements are much more important to our application and much harder to address. So hopefully you can accept the fact that from a logical perspective, SQL statements are a form of hard coding just as bad, just as serious, just as problematic as literal values. Well, then the question is, what do you do about it? Because obviously, you're not going to stop writing SQL statements in your Oracle applications. In fact, you're not going to stop writing SQL in your PL/SQL code, and you shouldn't, because PL/SQL is the best place for SQL. It is the easiest place to write it. It is the best place to optimize the performance of your SQL statements. So it should be written inside the PL/SQL layer. But the question is when, where, and how we should write these statements. And what you want to do is go back to basic principles. They should always guide you. And the most important principle, especially in the context of this lesson on hard coding, is never repeat anything. As soon as you repeat those literal values, you have to find them in multiple places and change them. And with SQL statements, as soon as you start repeating your SQL statements, just write them wherever you want to. Then you lose the ability to manage that application effectively and optimize it, and so on. So the fundamental rule about avoiding SQL hard coding is stop writing so much SQL and avoid repetition. And the way you do that is to hide your SQL statements behind a data access layer. Now, what this means really is a kind of a fundamental shift in how you think about SQL in your PL/SQL applications, and I recommend that you consider SQL a service. In other words, think of it as a service that is provided to you, not something you write. Today, for the most part, whenever you're about to get some data from a database table, you say, well, I need to write an SQL statement, and you start writing a select statement. If you need to do an update, you come up with the update statement. In other words, you're writing it all the time yourself, and as soon as you do that, as soon as you keep writing it and writing it and writing it, you and everybody else on your team end up with a lot of repetition and all the problems I've already talked about. So what you want to do instead is say, no, I need to get data. I'm not going to write a select statement. I'm going to find a function that gets the data for me. If I need to do an update, I'm not going to write the update. I'm going to look for a procedure that already does that update and call it instead of writing it. If you can't find a statement or a procedure that does what you want, okay, then you write it. You put it somewhere so that it can be easily found, reused, and maintained. And you build up a growing body of reusable shared code that executes SQL statements. So the service that I'm talking about consists of a set of programs defined in a separate data access layer. So you've got your presentation layer, you've got your underlying table layer, you've got your business rule layer. You should also have a separate layer simply for data access. There are several synonyms for this data access layer. Table APIs, procedures and functions that sit on top of individual tables and allow you to do a lot of the basic SQL operations through them. Transaction APIs that model your business transactions and provide high-level programs that perform those transactions. Generally speaking, data encapsulation. And here's the basic idea conceptually. I've got my high-level application code implementing user requirements. I've got my low-level tables with all the data in them. And instead of reading and writing every time I need to access those tables, what I'm going to do is put an intermediate layer in between my application code and my tables. This intermediate layer, the data access layer, knows all about all the aspects of my underlying tables and the relationships between the tables. So this layer of code knows how to do inserts, updates, deletes, all the basic stuff. It also knows that when I insert an order into my application, it's a complex transaction involving multiple tables. All that built into my access layer. And then my high-level application code does nothing but call programs inside this layer. And you never ever bypass the layer and directly access the underlying tables, either to query or to change. No. Instead, you always go through the layer, and then ideally, as the underlying tables change, you can minimize the impact on the application code and get many other benefits, which I'll talk about in just a moment. But that's the basic idea. You don't write a lot of SQL up here. The SQL statements are buried, predefined as much as possible in the data access layer, and then as you're writing your application, you just call those programs out of your big toolbox. So let's talk about some critical benefits of data encapsulation. First of all, and most importantly, you can change or improve your implementation with minimal impact on application code. Clearly, this is the ideal that you want to aim for. I add a column to a table, I add a foreign key, whatever, all this kind of change. And I buffer most of the change, the impact of that change, in my data access layer. Certainly, I will have to change my application code. If I change my underlying database, it's very unlikely that it wouldn't have impact at a high level. But I can buffer and hide most of the impact in my data access layer. Now, the reason I might need to do that is that the underlying data model is always changing. But also, Oracle might add new features, new way of doing things, and I want to take advantage of those really quickly. Or we simply learn new ways to take advantage of what's in the PL/SQL language. I'll show you an example of that in a moment. Second, vastly improve your SQL-related error handling. Right now, I think that most of us basically rationalize away doing very good error handling for our DML operations. For example, when I do an insert into my table, I really should check for null column values, dupe val on index, etc., etc. But what I usually do is rationalize and say things like, well, it's never going to raise a dupe val on index error because I've got a primary key and unique indexes in place. And it's never going to raise a null column value error because the Java program is going to make sure that there's always a value. In other words, I make assumptions, and those assumptions are the things that are most likely to fail on me and cause breakages in my application. So what I really should do is a lot of comprehensive error handling when I'm doing DML operations, but I tend to not do it because I'm busy. I've got a lot of things to do, so I skip over it. But with encapsulation, I can do a much better job. And finally, and perhaps most importantly, greatly increase my productivity.